So it's just three parts, basically: a large float, a cylinder, and a Pelton turbine. And the essence is that you use buoyancy, laws of Archimedes, instead of laws of Newton, and you're using the Pelton turbine, water to metal, lasting for 40 years. Of course, not everything lasts for 40 years. You have seals and stuff like that needs to be maintained perhaps every 50 years, etc. And there's, of course, lots of small things that have to have.
Hello, everyone, and welcome back to the CleanTechies Podcast. This is episode 70 of the show. I'm your host, Silas Maynor, and thank you for joining us on today's episode. Before we get into the episode details, a few notes and announcements. As always, a big thanks to our sponsors, NextWave Partners, for making the show possible. If you're looking for a recruitment partner across climate tech, ESG, or renewable energy, consider reaching out to NextWave, and their global team of talent experts can help you with those needs. From C-suite to engineering, NextWave can help you be covered. Also, if you are someone affected by the layoffs recently in tech, you can consider reaching out to one of their consultants. They've offered to do at least consultations with people to see if they have any advice for them on how to find another role, and perhaps, of course, have a role open in particular for that person. So do definitely reach out to them if you are affected, unfortunately, by the recent layoffs in tech, if you are especially looking to get into the climate space and make an impact. Their website is next-wavepartners.com or next-wavepartners.com, and you can reach them there. Also, if you are a founder in the space, please reach out to us, as we are glad to share what we can in terms of connections and partnerships and just linking people up with other people in the space. Always very keen to be very collaborative in this space. It's part of the reason why we started the show. I mean, generally speaking, the big reason is we wanted to share the technologies out there, and we want to advance the climate tech space. So we can do that as much as we can by introducing you to capital or other potential strategic partnerships. So with that, let's get into the show details. Today, we are joined by Jan Skjoldhammer, the founder and CEO of NoviOcean. And NoviOcean is a wave energy technology company that is developing what they believe to be a technology that will truly crack the wave power industry. And in this conversation, we discussed a number of things, including how he went from being a pilot to founding a wave power company, how the technology works, and how they combine the best of all different wave technology kind of individual items into the best package of the best assortment of all of them. How the layout and siting of the projects has to take place, and also the benefit of co-locating these projects with offshore wind projects. We talked about how the tech can help also reduce damage from waves onshore, and that's a quite interesting one. I had never thought that would be something, but because of the reduction of the height of the waves, they can reduce erosion on the shoreline, which is quite interesting as well. Then we also spoke about the importance of mobilizing regulators at a speed appropriate for the speed of climate change, which currently is a bit slow. They're not exactly in alignment. Overall, really cool discussion and opportunity to learn about wave energy, its history, and how NoviOcean is innovating in the space. So without any further ado, let's get into the episode. All right, welcome to the show, John. How are you doing?
Thank you very much. I'm doing fine. I'm in Sweden, Stockholm, where we now have our office, and nice weather. It's actually the warmest day ever in Stockholm this time of year, which indicates a bit, what we're doing, the need for climate change mitigation.
Mm-hmm. Just out of curiosity, what is the temperature that's the warmest day in Stockholm?
It's 14 degrees today.
14,
normally,
okay.
It would be like this time of year, somewhere between 0 to 5 degrees Celsius. So it's about 10 degrees warmer than normally. It's the warmest day ever in Stockholm this time of year.
Very nice.
So it's a good reminder.
Yeah, absolutely. The weather's been pretty nice in New York lately as well, too. So definitely an improvement from where I am originally from in Wisconsin. But I'm really, really excited to have you on the show here to discuss what you guys are doing. So why don't we start with just giving a quick introduction to yourself and kind of how you ended up in NoviOcean?
Yes, I'm actually Norwegian myself, living in Stockholm now for 20 years. My background is, educated as an officer and also have an economics degree. And then I went into flying. So I've been flying aircraft for about 25 years time, last 22 in SIS. pilot, captain, instructor, flying air shows even with all warbirds. Took one over from the US when I was 28, by the way. And then I've been working with race cars. I built my own race car and did that as a hobby for many years. So I learned a few things about what breaks and what holds. Okay. And then I had during my time many patent ideas when I was a teenager and going forward, and I saw this coming into the market 25 years later, time and time again, always irritating. And then after a business venture, I had some choices in life to make, so I decided to go for wave power.
So how do you ultimately get into wave power from coming from a background of flying airplanes?
Well, it's a technical thing. I used to fly, for instance, the largest Airbus, 300 tons, and I like machines and how they operate and how they're built. And then I did a large property deal while I was flying that went very well. And so that time I had some choice in life. Should I fly for 15 more years, do something more sensible in my life? And I had this sketch or solution for wave power laying in my drawer. And then I was thinking, am I going to do something more sensible than just flying aircraft? So I waited for them back for about 1 year. And then finally I kind of said, I'll go for this. So I resigned from this nice job I had, and then went into doing the wave power venture, working twice as much for half the salary, but it's meaningful and it's going to be real large over the coming years, it looks like.
Yeah, certainly. Well, I'm curious if there's any really big challenges you've had in making that transition, perhaps from a personal perspective or a technical perspective, any of the big things that you've had to learn kind of as you've transitioned into building this company?
Yes, it's interesting. It's kind of fun, at a certain age to change totally the career. To now used to work in my kind of close little family in aviation, and now going into business ventures, working with professors, engineers, doctorates, and attracting money by grants and also venture cap as time goes by. So it's different, and it's real fun, I think, because now my life is totally different when it comes to working, like what it used to be, and it's meaningful. I do this, as I say, 60% for the climate, because I think it's more meaningful. I'm not so young anymore, so the money is not that important, but of course I like to make a profit. And I think it's fun. Now I have a 6-person team at full time. We will be 8, I think, within not long. So it's just great to do something meaningful and fun in many ways, and working with science and heavy, complex pieces. I really enjoy it.
Absolutely. Could you maybe, to get things into the technical items a little bit, could you give us a quick history of wave energy in general, just kind of like the development of it, if there's any old technologies, and just kind of basically setting things up to go into NoviOcean?
Certainly, wave power is all. I think the first patent was filed in 1799, and I think the first person that got a kind of functioning was someone in France that I think like 1910 about made a oscillating water column running outside his house to make some energy, and then it's like more than 250 patents just in Europe since that time in wave energy. So many have had the hopes to make this successful. Many have failed. Many will fail. Why? Well, the ocean is very, very harsh out there. Waves can be up to 30 meters high. So many things get destroyed. And the other thing is to make it economical. So many systems are very heavy in relation to the output, and weight costs money. Also complexity costs money. So that's a challenge, and many have been trying different solutions, but for certain reasons, which I can get back to that later on, there are difficulties if you use certain principles to make wave energy economical, just the way you use the laws of Newton's and laws of Archimedes, for instance.
Mm-hmm, mm-hmm. And then I guess, could you, just for people who are unfamiliar with the technology as a whole, could you give us a really, really basic understanding of how does the technology work?
Yes, I would like to divide the systems into two categories. There are the ones that work with resisting the particles in the water. They move with, for instance, 2 meters per second, and you kind of resist them down to 1 meter per second, and you extract that energy. And the other systems are the ones working with buoyancy, laws of Archimedes, and that is by having air locked underwater as the water is rising, and then at a certain there's a depth you release the buoy, and you go upwards, and then you extract energy that way. So that's a kind of, you can divide this wave energy in many certain ways, but I would like to do that. And the reason why that's important is that our associate professor, who now works with us full time, has done very accurate calculations and showing that in our case, we're lifting 600 tons in every 4-meter wave. And if you're going to have the same energy by extracting just energy from the particles, which many do, then you need 30 times the area in the water. So that in our float is 38 times 8 meters. You need 800 meters times 10 meters of area in the water if you want to go by Newtons. And that's I would say a dead trap for many systems, because more than 50% of the systems are using particles. And in my opinion, it's very, very difficult to be economical with that large amount of metal in the water. So we're saying that you have to use buoyancy to be economical. I can go more into our specific solution, but it's simply buoyancy with extracting the energy connected between the seafloor and the buoy up there. That's how we get lots of energy in relation to the buoy. And this is important because so many people have been wondering, why hasn't wave power succeeded? This is, I think, the main reason. Many have been trying in the wrong end for many years.
Mm-hmm. Yeah, so could you go into the nuances of what NoviOcean is doing separately that's a bit different, that you believe is going to essentially make wave power successful?
Yes, there are several aspects there. First of all, we have to use buoyancy. That's the calculations are actually, you can see it on our webpage. You go into NoviOcean, look at document page, you will find a graph there showing this 30x factor. So we're using buoyancy. And secondly, our float is rectangular instead of round. And why is that? It's simply because you can lift 3 to 4 times more than you can with a round buoy by going rectangular. And the reason why it cannot be larger by a round buoy is that if it is too large a diameter, you'll be cutting the waves. Just like a large boat in small waves, nothing happens. So you can be about 1/3 at the most in relation to the wavelength. And that's in practical terms, that's about 10 meters width is where the limit is. So in our case, now we're going for the first 500 kilowatt, it is 8 meters width, and some of the buoys out there are 9 meters width. And by going rectangular, since the wave also is rectangular, you can lift more. So that's one thing. So first you have to use buoyancy, and you have to be rectangular in our opinion, because you can get 3 times more energy per buoy. And then if you're lifting 600 tons, 10,000 times per day, that's a huge, wear on all the mechanisms. So we have to have a system that can take this force. In our case, we use a hydraulic cylinder filled with water that pumps water up to a water turbine. And then you can ask, why an hydraulic cylinder? Well, think about your car. You're driving along, for instance, 80 kilometers. Something comes up in front of you, step on the pedal, 50 kilos, and you stop this car of 1,500 kilos in 30 meters. Next time, do the same speed, pull the handbrake, see what happens. Basically nothing, because that mechanical is just cogwheels and a wire. It's so much weaker. So a hydraulic cylinder is the best way to transfer huge amounts of energy in an effective way that lasts for a long time. It's used in every car, every structure, and the building machine around the world. So we use that. And on top of the system, we have stolen, you may say, the hydropower plant, the one you have up in every mountains in every country with that source. And those hydropower plants consist of a dam high up there. And then comes a tube down, perhaps 500 meters, within 50 bars of pressure. And that water hits the Pelton turbine, water turbine with high speed and high flow, which turns a generator on the same axle. So we have stolen that system, you may say, but on the top of the cylinder, top of the float. So the same pressure, 50 bars, for instance, and the same flow, in our case of the 2,000 liters per second, hits that turbine. That's 200 kilometers per hour. The Pelton turbine spins around. It's a very efficient engine, 90% efficiency, and water to metal lasts for 40 years. Metal to metal is much more tricky for this load to last for a long time. And also metal to metal will be much more heavy. So if you combine this thing together, the need for buoyancy, need to be rectangular, the hydraulic cylinder, and the Pelton turbine, you see also why mechanical lasts. And then finally, there are two ways to extract the buoyancy. You can go resonant. That means you're going up and down in amplitude higher than the waves, or you can go non-resonant, just going up half the wave. We're doing the latter. And that is because the first system is very complex to time since the waves are changing in length and height. I say often, it's like dancing with your worst partner. You're always inter-rhythm, outer-rhythm, constantly. It's very hard to time this. But if you go in non-resonant, just going down the lowest of the wave, you lock a valve, you wait for the water to rise on the side of the float. You're locking up to 600 cubic meters of air in the water. Then you open the valve, goes upwards. Much more simple to control, and the waves can change in height and length. It doesn't matter. So if adding all this together, you have NoviOcean, and we think we have superb numbers compared to other systems out there.
Mm-hmm. So just to kind of recap it to make sure I understand this correctly, just combining a number of different technologies kind of in the space and putting them together in the best arrangement, which is again including rectangular buoys and using the up and down motion rather than the particles, correct? Or buoyancy rather than particles. And then on the equipment side of things, using hydraulics rather than mechanical equipment in order to maintain longer lasting life cycle. And what's happening is it's pumping through this turbine, through every kind of up and down of the wave, is pumping this turbine and then creating energy, correct?
Perfectly correct. And so it's just three parts, basically: a large float, a cylinder, and a Pelton turbine. And the essence is that you use buoyancy, laws of Archimedes instead of laws of Newton, and you're using the Pelton turbine, water to metal, lasting for 40 years. Of course, not everything lasts for 40 years. You have seals and stuff like that needs to be maintained perhaps every 50 years, etc. And there's of course lots of small things that have to have service. But basically, the basic concept is very light. So we are in the range of about 130 tons, and we're extracting then on average 250 kilowatt out to sea, and that's compared to anyone else out there, is the highest energy output of any wave power concept in relation to weight, as far as we have learned. And that's very important, because go to any machine, garage or company, and ask for something being made in metal, and you ask for the cost, and the first question you will get back, you'll say, what is the weight? Then you give the weight, and then you say, the cost will be approximately that much. So the weight is a crucial element of reducing cost, and our system is very light due to the different principles there.
Mm-hmm. And out of curiosity, is there a specific type of arrangement on how these need to be deployed in order to maintain a consistent hydraulic flow through the turbine?
Yeah, good question. They will mainly be located on the west coast of the continents, because the winds are spinning the same way as the world, anti-clockwise. So the waves are building then over distance and time, and mostly from the westerly direction, from 240 to about 300 degrees in the main. Also some on the east coast, of course, but a bit less. And then you can arrange them in a pattern which are consistent with that wind and wave direction. So mostly they will be laying in two lines in our case, distance from about 200 meters from each other, and like overlapping, because when you have them working at full, you're killing about 30% of the wave. So we don't want to be downwind because you have a blanking effect. So they are in between, and in that way, in two rows, you can get lots of energy per sea area. Also, one interesting thing is California has problem with shoreline erosion. By having them more tight together, you can actually stop the waves from hitting the shoreline to a large extent. So you can get the best out of two things: green energy, which is very stable compared to wind power, and then protect the shoreline. Also, if I may add to that, we're also having developing a customer option with PV panels on top, which can fall out. So 700 square meters of PV panels, 120 kilowatt of those can be added to the system. And why is that important? Well, nowadays you have floating solar coming up as a common system, at least on inland lakes. Not so many to offshore because they can't take the larger waves. But even at the smaller inland lakes with the more moderate winds and waves, the cost of the structure and the cable is 75%. Well, we have already the structure and we have the cable. So why not combine them in a hybrid system? So it makes sense then. So the PVs are just 25% of the cost. So by adding this together, we can add to the value of the whole system. Also important because in the winter there are more waves, and of course more sun in the summer, so they're complementary. And an overcast day might be more wind, sunny days less wind. So in some way they can interact with each other and give more value for the same investment and same location.
Mm-hmm. Yeah, that is quite fascinating. I was curious to ask about when these are deployed. What does it usually look like, right? Because I'm assuming there has to be this kind of baseline structure that is able to basically be the fulcrum point, if you will. I'm not sure how to define this, of these buoys, because I'd just be curious to see what this looks like when it's laid out, even without the solar panels.
Well, the thing about the area, how it looks like, or you mean where it will be located?
Like the type of structure, also where it's located, right? Because I'm curious two things, like what does it look like? Is there a big kind of base structure that is the point at which these buoys kind of are attached to? How does that work? And then will this also affect any kind of shipping lanes or anything like that, depending on where they're laid out?
All right, good question. Physically, then you need to have a connection to the seafloor. So that will be, there are several solutions. There's the piles you can drill down, and there are suction anchors, which are used now in floating offshore wind, for instance, that kind of attached like a big vacuum pump to the seafloor. You can also have dead weight anchors and some other solutions. So depending what kind of substrate the seafloor is in. Then how they'll be located will be in strings, then laying with let's say the long sides towards the wave direction. So let's say if you look from bird perspective, you will see them in two rows, but every second will have a gap in between so that they don't disturb each other. And then location-wise, one thing is, of course, to co-locate them with wind power. Floating wind power, for instance, out to sea, because you have already the cable there. Cable is some expense. You have the subsystem, the connection to the subsea cable, and you have maintenance personnel there out to the same area, so it makes sense to have them together. And of course, there's one area to lease, not two. And then again, you have this overlapping in the timing, which is very important, because 40% of the hours of the month, which is a lot, there's basically no wind and zero sun power. That's 40%. So what do we do in those hours? We're burning fossils a lot, to the highest cost for the climate, as we all know, and for the consumer. That's when you're paying 40 cents per kilowatt hour, because there's a lack of sun or wind power. But the good thing is that they overlap. Now, first in the morning, you have sun coming up. Sun creates heat. Heat creates the wind. The wind creates the waves. But when the wind fades down, you have the largest battery on the Earth, wind battery, the waves. They remain for days. So in those hours, with the customer to the utility company is paying 40 cents per kilowatt hour, or they scramble to buy some liquid gas somewhere, in those hours, you do have wave power. And wave power can be then collocated with wind power, or if you like, much closer to land, because it's hardly visible, doesn't make any noise, and doesn't harm any animals at all. And most importantly, you can get 3 times the energy per sea area from wave power than you can from wind power, and it's much more stable. The base load of wind power, that means the lowest you extract per month, even offshore, is about 10 to 15%. The base load of wind or wave power is about 30%. Maybe I missed now, but the base load was wind power is 10 to 15%, and wave power is 30%. But the great thing is if you combine them too, the energy mix, because they have different, let's say, they're off-phased. If you combine them both, you can have a base load to 40 to 50%. So this filling the gap is so important, because nowadays that gap is filled by fossils. So what would you rather have? You want to fill that gap with fossils or wave power? It's an easy choice, isn't it? It's fossils or green power. It's both possible, and it's out there just waiting to be extracted for free, basically.
Yeah. So one question, I think you've sort of answered this already, but just to make it very clear, what is the intermittency issues, or what does the intermittency look like for wave power?
Yes, it is. It's like this. As I mentioned, the wind creates the waves over time and distance. So of course, when the wind fades down, which happens in half a day very often, then the waves remains for perhaps 5 days. Then they get slightly slower. Then normally the wind comes back again. So when the waves are fading down, the winds are building up. So then you have wind power providing green energy. And then the wind stops. Then you have wave power again there. So this changing of the time is so important. And of course, also, the sun power is only at daytime, but wave power works at night. So if you add this together, you have 40% of the month now powered by fossils, which you can power by wave power. How important isn't that? There's nothing else that can do it right now.
Yeah, that's fascinating. I think one thing I want to, if you could separate them without them being co-located, what is the levelized cost of energy for wave power versus, I think we should probably compare it to offshore wind.
Yes, a good question, very valid question. There are different numbers. The official numbers, let's see, from Ocean Energy Europe and other ones, state that the starting cost for wave power is normally from 350 to 600 euros per megawatt hour, from 30 to 60 cents then, if you like. And that's for the more common systems. But as I mentioned, many are ineffective. And that's why you have the high cost. Lots of complex metal in the sea, and you have this cost. Our techno-economical model, which are quite solidly made up of capex and opex figures and performance figures. They indicate that we're starting at below 200. That's the numbers we have right now for the first 3 megawatt area. Then after 10 megawatt, we should be down to about 125. Wow. And then, yes, I know it sounds like a fairy tale. And after 500 megawatt deployed, it looks like we, with the median learning curve, should be down to about 35. And this is for stable energy. So given, can we do this? The impact will be tremendous for the climate mitigation and also for the economical side. And the two things about that, which I would like to mention, that now for instance, the UK has now come with feed-in tariffs, or CFD they call them there, which then give tidal power about 210 per megawatt hour, 21 cents per kilowatt hour, if you like. And then should we then, well, wave power will most likely have the same or even higher feed-in tariff. So if we can produce energy for less than 200 and we get paid to 10 or more, we're going with profit basically from start. And all the islands, remote islands, 2,000 out there in the world nowadays, they pay them from 250 to 500 per megawatt hour for diesel. And they're also sinking in the sea. So they're very motivated for that. And all the remote locations. So in some way, you can go by subsidies, feed-in tariffs with the large utilities. For instance, in UK, and now also Canada has some in Nova Scotia, even better, about 300. Or you can go by the ones paying the highest price nowadays. That's not all, because if you are a utility company having wind power somewhere, then that utility company, perhaps they can produce wind power down to perhaps 5 cents at the best if it's a large, like Dogger Bank system, but more often it's like 10 cents per kilowatt hour. So I'm switching here between megawatt hour and kilowatt hours because you have American listeners, but I guess most understand the difference. But then when there's little wind, they have to buy fossils, don't they? And the cost of that fossil could be 300 or 400, or at least more than 200. So the value of wave power, even if it costs 200, is so much higher than just having wind power and fossils. So I'm saying that the value of wave power, even at 200, is so important for utilities to realize, because they can sell green power at a lower price, the same price as fossils, in the hours when there's no wind power out there or sun power out there.
Mm-hmm. Yeah, I also think it's interesting, worth noting and re-highlighting. If you mentioned specifically California has issues with erosion on the coast. This obviously there's going to be things that are done, that costs they have to mitigate this, right? So if this was done in a situation like that, perhaps it's kind of a 2-in-1 situation. Are there a lot of other areas in the world that you're familiar with that do also struggle with that issue?
We haven't dug down deeply on that, actually. We know about California, of course, because it's widely spoken about. But I'm sure there are other ones, and especially now, since now the sea level is rising. Then, of course, if they rise by half a meter and have the same waves as you had 10 years ago, with even higher waves nowadays, since you have more storms coming. Then, of course, this to dampen those waves with 30% is more and more valuable in many areas around the world. So I think this will be an added advantage for free. Basically, we can just deploy those rectangular floats that way. If they're round, it's more difficult because the waves tend to escape around the round buoy. But this functions like a wall, if you like, against the wall.
Yeah.
And
yeah.
30% does not sound much, but 30% of the highest waves, or on the high side, the energy, if you double the wave height, you quadruple the energy in the wave. So 30% of the waves will be perhaps about 50% of the damage done to the coastline.
Mm-hmm. Interesting. Okay, that's interesting. And then one thing I'm curious about is, can existing offshore wind deployments, things that are already going forward or already built, in the case of Europe, can this technology be added later on for a relatively low cost, or is this something that has to be done from the initial outset of the design, given the cabling, etc.?
Excellent. They can be added later on. Of course, if the cable is at the limit when there's high winds coming in, that might be a question if you can, add more to that cable. But normally, the wind power systems, the hours per month they produce 100% is very, very few hours. And the cables are most likely designed to take 120%, something like that, with some margin. So I would say normally the wave power can produce at full most of the time. Maybe have to, cut down or curtail now and then, but basically they can provide. So of course it's a large, let's say, with that way to combine them, and it can be done later, definitely. And also some of the structure, they also, taking some pain, you might say, from the slashing waves coming into the structures, even the floating ones. So if you have wave power ahead of those on the upwind side, you could also mitigate the waves slashing into those structures. So it's a possibility. So it can be in the same area for sure.
Mm-hmm. So aside from the testing that I saw that you have doing on your website, are there any pilot projects already existing that have been deployed or you're working on?
Yes. Well, we've been doing the 1 to 6 scale, then the 1 to 5 scale, tested in the wave tank in the UK and in France, and also been out to sea for a total of 5 months. It actually worked perfectly well from day one with the system. Of course, there are always things you have to fine tune and let's say, but the principle was there from day one. And now we are going from TRL 6 into TRL 7. Meaning that we're now working on the full-scale design for the 500 kilowatt, and it will give 500 kilowatt, as mentioned, in 3.5 meter waves. By the way, talking about the kilowatt thing, it's I have to go into that. So many in this sector talk about rated power only, and it's like having a sticker on the back of your car saying 1,000 horsepower, and it has 100. It means very little. It is the average annual delivery which pays the bills and gets their revenue. So in our case, we're saying 250 in average outside, locations like California or Portugal, Spain, and some more in Oregon and Ireland, for instance, and some less when you get closer to the equator. We can give, in theory, up to 1 megawatt, if you like, in waves of 5 meters. But they are more seldom, so it doesn't make a big difference for the annual thing. So we just, so far, we've named our system 500 kilowatt. But anyway, it's more than anyone else in the average delivery there. So anyway, that was a sidestep. But we're now going into working now with ship designers for designing of the float, 38 meters long, 8 meters wide, 4.5 meters high, 1,600 tons, and other parties then for the cylinder and for the turbine and generator side. So we are moving more and more into that with our staff, and will be, I think the design on the float should be ready within 9 months about. Construction starting in about 1 year from now. Should be in the water within 2 years on the float. That goes in the water on the west coast of Spain, France, or Portugal. It hasn't really been decided yet. We are talking with the test sites. And then that goes in the water for a winter and testing the anchoring, the winches, and the measuring forces. And then in the meantime, we're working on the power takeoff. Power takeoff is a name for the machinery, by the way, if anyone's not familiar. And then that goes into the middle of the float after 1 year in the sea with the float. So in about 3 years' time, we should be deployed with the whole system out there. Of course, money is also a time factor. This is with a moderate funding with grants and venture cap or partners. Should someone understand the impact of what our system can do, be it utility companies, oil and gas companies, or philanthropists or venture cap, we can do it in 2 years with more money. So now we are just opening up with saying we would like to see about 8 to 10 millions coming in over the total of the coming 4 years. Valuation for the company between 50 to 60. We give some leverage there so people can see where they want to be themselves. But if someone understands there's a potential of wave power and our system, and they want to really mitigate the climate change soon, see our system out in the thousands in the coming decades to make a big change, most welcome to give me a call.
Absolutely. I think it's interesting you mentioned that the funding you're seeking is actually a pretty low number comparatively when you're looking at a lot of energy tech, and especially compared to some of the costs of offshore wind. So I think it's certainly worth people reaching out if this is of interest. One thing I did want to also touch on is, what are the regulatory issues or concerns that you have to face, or maybe it's just in particular regions? I'm always curious to understand the regulatory concerns.
Yes, it's I almost say it's a pain in the ass, but I shouldn't say that on radio. But of course there are regulations and they're needed. There are two sides of the coin. Of course, you have the certification of the system, which we have to follow, like with any ship or any offshore design. So now we are starting working now with Lloyd's to look into the whole process there. We're also working with the DMEC in Holland to be going to all the technical requirements during the design phase as well, so make sure we do everything right. So that's one thing on the system itself. The second is the consenting process for the locations out to sea, because you cannot deploy, of course, anywhere. Same as with wind power, you have to go through the applications with the local region, and they have to look into what you want to do in how large area, how is the impact on the marine life, which is of course important. Shipping lines, are they obstructed? How is by the fishermen's area? All that has to be done, and that is some issue which has been worked on by Ocean Energy Europe, for instance, because it takes too long time. So right now we're trying this as a force together to try to speed up those processes, because our development and the climate change mitigation cannot wait too long. So having a 5-year consenting period should be down to half the time to make this being available around the world and mitigate the climate change.
Mm-hmm. Yeah, I do think it's fascinating, the regulatory concerns and challenges that a lot of people face. Obviously, it's extremely difficult if we're trying to solve these problems. We do need to move quickly, right? And normally government being involved is kind of the antithesis of quick, which obviously in some cases for a good reason, right? But that is interesting. But in terms of regulatory concerns, there's a lot of things. I know, like in offshore wind, floating offshore wind in California, I believe there's something like 32 permits or something that are required. What are the typical permitting? Because you mentioned there's no damage or harm to wildlife or anything like that. So I just want to understand, like, what are the differences here? Because it sounds like it's a lot less things to go through.
Well, the wind power turbine consists of 8,000 parts, and they have, for instance, very advanced synthetic oils on board, which if they leak into the water, it's not good. And in our case, we have much less parts, and we do, of course, have some fluids on board, but to a very low extent. So I think we're kind of lucky in that way. It should be a bit easier with the licensing of the system certification. So we do hope that this process can go quicker, but of course it must always go through some procedures to be accepted by all the, let's say, instances that need to have a say. For instance, the fishermen, the marine biologists, and so forth. So that's fine. But I would like to compare this to a war, because in the Second World War, you had a lot of issues that need to be resolved quickly to be able to win the war. So in just 5 years, you made new aircraft types and new, submarines in short time. I can guarantee you that these systems were approved quite quickly to be able to win the war. Right now, we have a war against the climate change, and we are really on the back foot already. So I think lots of governmental agencies and also venture cap and others see this thing coming, and that should motivate them to say, let's speed up, let's simplify, let's get this thing done. Because if you play like we did in year 2000, that speed, okay, we might have a real problem, much larger problem in some years. So I do think that the also governmental agencies do realize that we have to speed this up. We cannot delay our system and others unnecessarily for years. So I hope to see that. I think we'll see it actually.
Mm-hmm. Yeah, that is an interesting observation. I think it's something worth kind of like you can take a page out of the book of China, right? They were able to deploy a lot of different things, maybe not necessarily green technologies, but they were able to deploy things very quickly comparatively to, countries like the United States, for example. And I think it is necessary for us to have, how I like to say is, the agile methodology, but applied to policy, right? So it's like, you try things out, and if it's wrong, you fix it very quickly, right? And it's about that active feedback, which I think that usually is my beef with policies, right? You set this policy in place, and then you've got this policy going on for decades, right? Where it's like, hey, perhaps at some point this wasn't actually necessary. I know, just a quick funny story is where I'm from. There was this law created way back in the day where it was illegal to throw snowballs. And it was a bit of a funny bit when people kind of found out about this. But point is, it's a kind of an out of date law. But any final thoughts you want to offer us to close off the conversation here? Perhaps people wanted to get into the space where they might, what educational route they might pursue, etc.
Yes, if I may comment one thing more on what you just mentioned, that on the Chinese, for instance, we had COVID, which was an immediate crisis, and humans are kind of good to act quickly on immediate dangers. So they built a hospital for 10,000 people in 3 weeks. So that's into the money thing. If you have money and you have the crisis enough, things can happen quickly. But humans are kind of bad when it comes, things happen slowly. That's why we're still burning more fossils now than we did in 2015 when the Paris Agreement. So it has to be up in your face. So, but given then we have more money and more will from the political side, it can happen more quickly. And basically, I would like to invite people, look at at our homepage, just Google NoviOcean, and you will see what's there. Look at the document page, you will see presentations there. And also, of course, listen to the podcasts on there and look into the media page. And finally, if I may, end with a quote from Larry Fink, the BlackRock CEO. This is for the venture cap and the potential partners. He stated that the next 1,000 unicorns won't be search engine or social media companies. They'll be sustainable, scalable innovators, startups that help the world decarbonize and make the energy transition affordable for all consumers. We think this will happen with some companies in our sector, might be ours. Thank you.
Absolutely. I think that's a great way to end it. Obviously, definitely encourage people to get in touch. And, if any companies are interested in partnering or funding, getting involved in this, I think it's great technology, licensable and very, very interesting. So thank you so much, Jan, for coming on, and looking forward to continuing and following your journey.
Thank you.
Thanks so much for listening to today's episode. Please let us know what you thought of the show. We're always keen to hear your thoughts and feedback, maybe any potential topics you'd like to hear in the future. And if you want to continue the discussion about this topic today, feel free to reach us at the various ways. Probably the main way to do that is either over LinkedIn, Twitter, or via Slack. If you want to join the Slack channel, you can reach me there very easily. And then, please, of course, if you find this interesting or know somebody that might find this interesting, we ask that you please do share this with them. Just think of 2 people that might be interested in this technology and at least hearing about something like this, and then just drop them a text with it. It's really, really helpful to spread the show. Just a couple shares at a time. It's very, very helpful. So thank you for doing that as well. And of course, we encourage you to reach out to John on LinkedIn and to learn more about NoviOcean through their website, especially if you are a potential investor looking into wave energy technology. It could be very interesting for you. And if you are joining us for the first time, we ask that you please subscribe and turn on notifications to be made aware of episodes in the future. We really appreciate you following us along on this journey. And especially very, very important, if you did enjoy the show, we really, really appreciate any reviews that you want to leave us, especially on Apple Podcasts. It's very, very helpful for us to get more awareness about the podcast out and around. And then for a quick note on our next episode, we will be joined with Sharon Murray from the Good Food Institute, or GFI, and we speak broadly about what GFI is doing as a nonprofit to advance the alternative protein space, as well as discuss the nuances of the alternative protein space as a whole, including what are the challenges, how does it work for non-scientists, and the path forward to make this possible. So super exciting episode, and I'm looking forward to being able to share that one soon as well. Sharon was a really great guest and went into a lot of great detail in a way that was extremely simple to understand for a space that is very, very technical. So that was it's a great episode. Stay tuned for that one. And again, thank you so much for tuning in to this episode, and we will see you next time on CleanTechies the Podcast.